All right. Hello, everybody. Name is Lorenzo Riano, and I work for Anki. So we are a robotics and AI company, and we bring life to physical devices. Our core technology is vision sensing in AI and robotics, but on top of that, we have developed animation, design, interactive user, and content. This is an example of a storyboard that one of our designers uses to give our robot a character. And you can see there is a backstory and there's all kind of user interactions that are designed for the robot. Well, our animators use Maya to develop animations and to render them on the hardware, so to realize these animations on the hardware. And this is, as far as I know, the first time that this has been implemented. And actually, this is what convinced me a couple of months ago to join the company, this blending of artists and engineers. Under the hood, we have vision and known technologies. In this case, robot is using vision to find the cubes and to locate them in the environment. We also have developed components like path planning, navigation, and localization. We are a bold company. Our goal is to develop Rosie robot, and we started with entertainment. We're developing more and more complex robots as time goes forward, and we already have shaped hundreds of thousands of robots worldwide. We're hiring for all different roles. We're hiring for full-time and interns, and if you're interested, please come see us at the booth outside. Thank you.
Hi, I'm Felix from Bosch. I work on motion planning for autonomous cars. So at Bosch, we work on a complete solution for fully autonomous driving. And that means we build dedicated sensor technology as well as building a vehicle platform and an algorithmic AI. So our current project that we work on is building a vehicle that could, for example, be used for a robotic taxi service. And we do this in collaboration with Daimler. So our office in Sunnyvale focuses on software components. That means working on a fail operational localization with multiple modalities, working on sensor data fusion with high resolution sensing and 360-degree vision, and planning with developing new technologies and new techniques for decision-making. So all of these areas obviously involve very challenging problems from robotics. We are hiring, and if you're interested in any of those areas, please come and talk to us at the booth.
So, hi, my name is Jürgen Hess. I'm a researcher at the Bosch Service Robotics team that we also have in Palo Alto. And we are focusing on the future of industrial manipulation. So here we want to really make industrial robots more flexible, quickly deployable, and easily teachable by the human user. And hereby we focus on really the real industrial use cases that we derive from our 270 plants that we have worldwide within Bosch. So we focus on really skill learning for industrial insertion tasks that can range from packaging to really tight fittings in manufacturing, and also on industrial perception. So really challenging in perception of parts that are shiny, do not have texture, and are reflective. Now, our team started with a peer-to beta program, and so we also continue to work together with the Open Source Robotics Foundation. And I also want to say, so if you are interested in really pushing forward industrial manipulation, come and talk to us, and we have open position, intern positions, as well as associate positions. And also not only you get to work on exciting stuff, but you can also publish your result with us.
Hi, I am Pulkit, and this is joint work with a lot of collaborators at Berkeley. So we humans, when we observe someone perform a complex task, such as manipulating or tying a knot, we can very easily copy it by just observing one demonstration. Right? So we set out to see if we can also build robots which can observe just RGB images of a person performing a task and then replicate it. So what you see over here is like the robot trying to replicate what the human was doing. So for example, over here, the arm comes in and he tries to tie a knot. And the robot just observes the RGB images, and then it tries to replicate what the robot actually did, or what the human actually did. And over here you see it's able to tie this knot. Right? So the main idea of our work is that we build a model. We use the interaction of the robot to build a model which is makes the forward and inverse dynamics consistent. And our accuracy goes up to 65% from 38% as compared to previous work. Thank you.
Hi, my name is Sylvia. So in motion planning, typically, if we have an environment and some obstacles and a goal, we can very quickly find a path to the goal, but this path might not be dynamically feasible, so we may crash when we try to actually follow it. What we do often in robotics is expand this obstacle by a heuristic error bound, which is great because it reduces the chances of us crashing, but there's still no guarantee. So we propose modeling our system as having a planning model, this very excessively simple planner, and having a tracking system that tries to chase this planner. We do a differential game between the two systems, which provides us with the maximum possible tracking error bound between the two systems, as well as the optimal error feedback controller for our realistic tracking system to try to chase our planning system. This means that in real time, we can sense obstacles, expand them by this guaranteed tracking error bound, plan using our simplified real-time path planner, and then follow it using our guaranteed safe error feedback controller. Oh, okay. So these are supposed to be equations. Here's our simulation. I'm happy to talk about more simulations or hardware demonstrations at my poster. But this means we can do real-time planning and navigation safely, which is cool. Thanks.
Hi, I'm David. So just jumping off of what Sylvia was talking about, just a quick recap. So what Fast Track lets us do is plan trajectories on a sort of small, low-dimensional state space easily in real time and then track them safely. But the problem is that often these guaranteed error bounds are quite conservative. So how can we reduce this conservativeness? So what we did is oh boy. Okay, well, what we did is we wanted to consider what happens if we use multiple different planners kind of in our head at the same time and can trade off between them at runtime. So, so this should look a little bit better, but on the right-hand side, what you'll see is two different error bounds for two different planners, and the way that we can sort of easily get ones that are different sizes, just imagine we let the planner move at a different max speed, for example. So the slower it moves, the easier it is to track. So what that looks like here is we now have two bounds that we can imagine, and then plan a path where we transition to this smaller bound, essentially. So then when we track it, we go slower and then speed up. So for...
Notice that the tracker always remains inside the tracking error bound,
okay.
Even when the...
Anyway, so we tested this in simulation. It works great. We tested it in hardware. It also works, so that's cool. Yeah.
Hello, everyone. I am Saurabh Gupta, and I'm here to talk about my work on cognitive mapping and planning for visual navigation. Let's say we are given a robot that has been dropped into a new novel environment that it has never been in before, and we want this robot to be able to move around. Let's say go to a particular point in space or find objects of interest. So go and find chairs. This is obviously an important problem and has been studied in robotics extensively, but the dominant solution that has come up is this problem of solving a mapping problem, which is to build a precise 3D reconstruction of the world, and then solving a path planning problem, which is to use this precise reconstruction to plan paths in the environment. What we're trying to argue in this work is that a precise 3D reconstruction of the environment is both are necessary and not sufficient for solving the task of visual navigation. To address this issue, we have come up with a novel joint architecture for doing visual navigation. It's a neural network-based architecture which has a mapping module which generates a spatial representation of the world which can be used for planning. And everything can be trained end-to-end, leading to representations that are custom to the task of visual navigation and can lead and are geometric because they are spatial, but at the same time also carry semantic information which allows you to make predictions about spaces you have not seen. We have done experiments on real robots where we are able to see that this works effectively with monocular RGB cameras, and I'm happy to talk more at my poster. Thanks.
All right, I'm Ed. This is traffic weaving. So this is a very stressful scenario for humans. I don't know if you can tell, but there's the end of the road in about 100 meters, and you've got to swap lanes with cars next to you and figure out how to, get past each other. So how do we get our robots to do this? Basically, we gathered a large data set of about 1,000 trials of humans doing this with each other. We trained a mixture model that learns human action sequence distributions conditioned on both interaction history and your candidate future robot action, what the robot thinks it might try to do. And basically, I'm going to show you a couple of plots of longitudinal acceleration, relatively common things that you would expect happen. If we plan to accelerate a lot, we think the person next to us might slow down. If we slow down, they might speed up. If we wait and see, we see two modes. They might do maybe either one. So what do we do with this? We try essentially an exhaustive search over candidate actions for the robot. Click. And it works pretty well. And all of our code and data set is open source. So if you guys want to check me out at the poster, the link is there.
Hi, so I'm also working with Marco Pavone, and as he introduced this morning, we're interested in modeling tasks specifically from the risk-sensitive framework, where we want to capture events of low probability but increased and high sensitivity costs. So specifically, we're looking at the interaction setting where there are humans also involved in the environment, and we want to be able to predict and be able to infer what their actions are going to be over time. The standard framework, of course, is inverse reinforcement learning, but this normally assumes that humans are acting on minimizing an expected cost over time. But this has been shown to be a poor model for modeling humans, specifically in risk-sensitive scenarios. So instead, we replace the expected value with a coherent risk model, and I can talk about these properties later on. And we can show that we can come up with a linear programming algorithm to not only back out the cost function for the humans, but also model how they behave in risk-sensitive scenarios. We tested this in a driving simulator game where the humans were instructed to try and follow a leader car to see how accurately they could try and track this car without crashing in. And we were actually able to see a range of responses and be able to back out their risk preferences. And the slide has frozen. It's frozen.
Exciting times. Okay, was that all?
Yeah, I mean, that was just a play. Okay, and we were able to capture a wide range of responses. This is me driving, being very risk averse, and there are also videos of risk neutral drivers who were a lot more aggressive in their driving styles. For example, the speaker before me, and I can come and talk to you about this a lot more in detail. Thank you very much.
Hi everyone, I'm Sharon, and working with Dorsa. I'll be presenting our work on human-human collaboration on sequential decision-making tasks. Humans and robots collaborate to explore and navigate uncertain environments, but often they have different information. We can abstract this into sequential decision-making tasks. These we can formalize into multi-arm bandits. Let's say we have K arms with different reward rates, giving 0 or 1 for pulling an arm in the Bernoulli case. The decisions we make on which arm to pull trade off between exploration and exploitation. It turns out we humans are suboptimal at this. Is this mic working? Are suboptimal at this because we have limited memory, and honestly, we can be quite risk averse. However, we can model the suboptimality with an algorithm called knowledge gradient. If we explore arm K at time t and exploit right after, we can take the expected value over all possible arms and subtract out the value of exploiting at time t and compute the knowledge gradient. We can then reweigh this value by time, favoring information gain earlier on. Experimentally, we ran a study on 13 participants on about 260 Bandit games, and we found that the predictions by knowledge gradient agreed with humans 77% of the time. Okay. We're also exploring collaborative settings with asymmetric impartial information. And come check out our poster. Thanks.
Hi, I'm Andrea. I'm going to talk about how robots can learn from physical interaction with humans. So consider this robot. It's moving from a start to goal by optimizing this objective. And now consider that because there's a human in close proximity, and the human has decided that they actually don't like how the robot is performing this task, and they're going to physically interact with the robot. Now here, in this traditional method, the robot is continuously resisting the human's force, and the robot is going back to its original trajectory that it's optimized. In this work, in contrast, we say that human interactions are intentional and informative, and thus give the robot useful information about its true objective function. We formalize, okay, so there's a lot of math there. We formalize reacting to physical human-robot interaction as a dynamical system where the robot has uncertainty about its true objective, and the human interactions give it information about the true objective function. So here we derive an online approximation for the solution to the optimal policy, and we have the robot being able to replan and learn from physical interactions online.
Hi, I'm Dylan Hadfield-Manel. Earlier today, you heard Anka Dragan talking about how reward engineering is hard, and we presented some of our recent work. So here you have a boat that's supposed to be winning, but instead it's getting points. And we presented some work on inverse reward design to try to solve that problem. So here you have a designer who has a model of how a robot's going to behave. She designs a reward function, and then the robot goes into the real world, and hopefully it avoids unexpected things. So what's the sort of best we can do from this type of systems? We've got a person with a model of a robot, and then what do? We put that model inside of a robot, and we have the robot respond to that. But then, now the system designers are going to get better because people are smarter, and so we're going to keep going, and you can sort of see where all of this goes. And eventually, this boils down into something that we are calling cooperative inverse reinforcement learning, where you have a robot that has a set of things that a person might be interested in, and a person who knows what they want and has a set of actions they can take. This is a really, really hard problem because it's a POMDP, there's partial observation, a whole bunch of things. But we figure out a pruning rule in some recent work that allows us to compute the optimal solution to these games much more efficiently. Here's a picture of us pruning some stuff. It's efficient, and the way I can show you that is we save a bunch of time, we can solve a bunch of bigger problems. We do it faster, we get higher value. Come to the poster to find out. Thank you.
Hi, my name is Kunal Menda, and I'm with the Stanford Intelligent Systems Lab. I'm going to be talking to you about one of our recent works called Dropout Tagger, which is a Bayesian approach to safe imitation learning. So many of you are probably familiar with the imitation learning problem, where you're trying to copy the behavior of an expert policy onto, say, a novice neural network policy. One of the problems with doing this naively is the problem of cascading errors, and so many of us turn to the Dagger algorithm to solve this problem. But when you're interacting with the environment in Dagger, there's essentially a weighted coin toss that decides whether the action of the expert or the action of the novice is used to interact with the environment. And this can be particularly bad if you're in a highly risky state. So the way that we address this problem is by making the assumption that in many cases, you can correlate the risk of a state with the familiarity of that state. And so if we train the novice neural network as a Bayesian neural network, then we can approximate the behavior of a Gaussian process. And so by doing this, if we find ourselves in an unfamiliar state, then we can use the variance on the novice policy's action distribution as an indicator that we should transition control back to the expert, and thereby getting a much safer decision rule. Thank you.
Hi, my name is Masha Itkina. I am also with Professor Michael Kokendorfer at the Stanford Intelligence Systems Laboratory. In recent years, deep learning has had tremendous success with image-based data, all the way from classifying cats from dogs to video frame prediction, which you can see in the top figure here. So the way to look at this is we're looking to predict our future video frame given our previous frames. So looking from left to right, the top is our actual measurement from our camera sensor, and the bottom would be the prediction. And this has been done with something called PredNet network architecture. What I'm interested in is applying these highly successful deep learning methods into the field of autonomous driving. Specifically, one of the key tasks for autonomous driving is planning when you are in a very occluded, very cluttered urban environment. And in order to plan well and safely, you need information about the future state of your environment. And what we can do is we can utilize a similar architecture as in video frame prediction to instead predict from LiDAR data. So predict from our occupancy grid maps that give us a top-down view of our environment and be able to see what our future state of our environment will look like and plan accordingly. If you'd like to learn more, please come visit my poster. Thank you.
Hello everyone, this is Burke Alton from the University of California, Santa Cruz, and I'll be talking about our project, Computationally Aware Cyber-Physical Systems. Our objective is to generate new fundamental science for CPS algorithms which adapt to the computational constraints imposed by the platforms. Algorithms which employ high-fidelity models can overload the computational part of the system, which in turn can lead to the input to the physical system being updated in a delayed fashion, potentially violating safety. So our research efforts seek to trade accuracy by performance by taking computation explicitly into account. Receding horizon approaches are specifically computationally intensive due to using prediction and optimization concurrently. One of our most exciting findings is that hybrid dynamical systems tools can be used to overcome computational constraints. We proposed a model predictive controller scheme that is fairly general, and it models the computational events explicitly. Under appropriate assumptions, the resulting closed loop has a robust stability property. We also applied this theory to the UAV system that drives our project by developing a set-based model predictive controller strategy. So please come by our poster. I'd be happy to discuss more. Thank you.
Hello everyone, my name is Ricardo Spiga, and today I'm presenting a joint work. I'm from Stanford University, and this is a joint work with actually the University of Zurich and the University of Saragossa. So I'm going to talk about autonomous drone racing. So drone racing has become very popular over the last years, both among hobbyists and among researchers. And apart from the very cool videos, we think that autonomous drone racing is a very interesting research problem because it poses a number of challenges in terms of perceiving the environment, being able to plan trajectories, do optimal control, and so on and so forth. But the aspect that we are most interested in is actually the interaction between different players, because in fact each player wants to win the match, but they also have to avoid each other. And because they cannot or do not want to communicate each other's intentions, this is kind of very tricky. And because of this, actually, a number of things that we can learn from drone racing can actually be applied to autonomous driving, right? Where you take away the competition part, which it's not supposed to be there, but sometimes it is. Well, you have a similar problem in that you're sharing a road and you want to avoid collisions with other agents, but it is very tricky to communicate intentions. So, okay. I'll just skip this slide for a reason of time. So the trick is to be able to predict other agents' motion. Well, this slide is completely messed up. Well, we use Nash equilibria, and the cool thing is that we are able to compute Nash equilibria in real time, and you can see that we obtain some very interesting natural behaviors that emerge where actually players can exploit each other collision avoidance to win the race. Thank you.
Hi, my name is Zijian, and in this work, we propose a set of controllers that enable a group of robots to collaboratively transport a common payload in both 2D and 3D. Our approach features using no inter-robot communication. Instead, the robots can locally measure the motion of the object to get an indirect sense of the forces applied by the other robots. We show that this indirect information is enough for coordinating the robots. In the video below, it shows an example in 2D where 4 omnidirectional robots move a payload. There's only one leader robot who knows the desired trajectory, and 3 follower robots have no information about the task or the other robots. They can, using the local measurements, they can still synchronize their forces to the leader's input, resulting in a coordinated motion. We further extend our approach to 3D with a fleet of rigidly attached colloters, where we assume that each colloter is aware of the desired trajectory. This allows each colloter to compute the total desired range. But the challenge here is that the long moment arm kind of prohibits the colloter to apply range along a certain axis. So we address this control allocation problem by letting each colloter solve a local optimization which finds the best action locally. And collectively, we show that this local actions lead to achieve the global desired range. So please come to see me at the posters. Thank you.
Thanks to all the fantastic students, and sorry to rush you. We'll take a coffee break now for half an hour. We'll reconvene at 11:25. There is coffee over there. Talk to our sponsors over there. Talk to the students a little further down the hall.